Uh, Hello. Today I'm gonna present sparse instance actuation maps for real-time instance segmentation. Okay, so instance segmentation, its purpose is to generate instance level segmentation for each object in an image. It's different from semantic segmentation, which categorizes the objects. So a tremendous breakthrough is achieved solving this problem with CNNs and object detection. However, developing real-time and efficient segmentation model is still challenging and urgent, especially for autonomous driving and robotics. So the common methods to do this task is to use detectors to localize objects first, and then segment through region-based neural networks and dynamic convolutions. But these methods are heavy for real-time segmentation as they use dense answer for every instance. As a result, they bring redundant prediction and computational burden. Secondly, the recent works require multi-level prediction for instances with different scales. So the scale is also a problem in here. And to deal with that, like we have to use multi-level prediction. And the post-processing for mask processing and sorting for dense prediction. We also need post-processing for the other common methods, which also requires time and computation. So in this paper, I'm going to present new paradigm. Instead of using boxes or region centers to represent objects, the SparseInst introduces sparse set of instance actuation maps to highlight informative regions of the objects. Instance actuation maps are instance-aware weighted maps, and instance-level features can be directly aggregated according to the highlighted regions. Then recognition and segmentation can be performed on that output instance features. Benefits of using SparseInst. The implementation is simple. It has a very simple pipeline and just matrix multiplication and convolution. And it can adaptively highlight informative regions of the objects, and we don't need to use answers. So in terms of object representation, the existing methods can be divided into two groups. First, the region-based methods, as you can see in here, it relies on object detectors to detect objects and acquire bounding boxes. Afterwards, we apply ROE-align to extract region features for pixel-wise segmentation. This is a faster CNN model. This is a very popular model to extract features and segmentation. In mask RCNN, it actually extends fastest RCNN by adding mask branch to the predicted masks and objects and offers strong baseline for end-to-end segmentation. So this is a region-based method. And in center-based methods, it's more slightly improved than the region-based methods. Single stage, answer-free objects, answer-free detectors that represent objects by center pixels instead of bounding boxes, as in here, and segment using these center features. For example, Solo is a detector-free method that localizes and recognizes objects by centers, as well as generating mask kernels. but yet SparseInst has simpler pipeline and higher efficiency. So here is the pipeline of SparseInst that contains 3 components: backbone, encoder, and instance activation map-based decoder. We will come to this later. So in backbone, we use we extract the multi-scale image features using ResNet 15, and it generates image features. So instance context encoder is attached to the backbone to enhance more contextual information and fuse the multi-scale features. I think this is the most famous. So we have here convolution 3, 4, 5. Each has its dimension. These are image features. So in encoder, objects with wide range of scales are problem. So we have, and it also degrades the performance of the detector. So to deal with this issue, we use the model uses multi-scale feature fusions. In other words, feature pyramids. The one problem is multi-level pyramidal features increase computational burden, especially for detectors using heavy heads, as well as producing amounts of duplicate predictions. But SparseInst aims at faster inference, leveraging single-level prediction. So in response, the instant context encoder adopts a pyramid pooling model. Okay, so pyramid pooling module. The extracted image features from ResNet are divided into multiple spatial beans with different scales, as you see in here. So within each spatial bean, a pooling operation of an average or max pooling is applied to aggregate the information. So in our case, it's, as you can see here, 3x3 convolution. After pooling, the output of from each bean are concatenated or aggregated in some manner to create single feature representation that encompass the information from multiple scales. So as you can see in here, these are image features, and then the pooling and convolution is applied. And we have, for every scale image feature, we have the single dimension feature, and we upsample it. In other words, for example, in here, we have the dimension of this. So we apply pyramid pooling, in other words, convolution, and then we upsample it. For example, multiplying 4 of each dimension, and also in here, we, for example, multiply by 2, and then we see 4, we concatenate and apply convolution, and at the end, we multiply by 2 again. So in the output, there will be many like sheets of like this, and we concatenate it. So that's what pyramid pooling is. In decoder, for example, instance activation map-based segmentation decoder, which contains instance branch and the mask branch. Here, the 2 branches are composed of stack of 3x3 convolutions with 256 channels. The instance branch aims to generate instance activation maps and n instance features for recognition and instance-aware kernel. N here is set by hours. It's a parameter, number of objects, for example, 1,000. The mask branch is designed to encode instance-aware mask features. In here, so we'll come to this later. Okay, so instance activation maps. So we have the input image of this dimension in here. Instance activation maps is simply a function, FIAM, here, where A is a sparse set of instance activation maps, A here output, and our function is a simple network with sigmoid nonlinearity. In here, as you can see, dimension with the depth changes. And this one is like n instance activation maps, actually n dimension, n depth. So we can obtain a sparse set of instance features by gathering distinctive information from the input feature maps X to the instance activation maps through this one. So here A is a set of n instance activation maps, and Z here, it's a feature representation for n potential objects. Z here is instance features, for example, yeah, here. And A here, actually not A, this one is normalized to 1 for each instance map. So sparse instance aware features Z are straightforwardly used to consequent recognition, instance level segmentation. So Z here we can use this directly for segmentation and classification here. As you can see, Z has a dimension of n by d. Here, n is like the number of objects. D here, like a normal feature, image feature depth. So in decoder, acquired instance feature Z, you previously have seen, like in which each open potential object is encoded into 256D vector, like the D. Then the 3 linear layers are applied for classification, objectness score, and mask kernels. For example, here, this is instance activation maps, and then we have this one, A here, and then it's the 3 linear layers are applied. For example, each one is here, here Z, and these 3 linear layers. To obtain fine-grained instance features, we present a group instance activation maps to highlight the groups of region for each object. Multiple activation maps per object. Specifically, we adopt 4-group 3x3 convolution as our F for group instance activation maps and aggregate instance features by concatenating features from the group. So the previously, we get the instance activation features for each object, but in here we apply it in group, for example, like 4-group before concatenating it. As a result, we can get, for example, multiple activation maps per object. If we apply this in group, like, but previously it's for a single object. With instance-aware kernels, WI, generated by instance branch, the segmentation mask for each instance can be directly produced by M multiplied multiplied by M. Here, M is a is predicted mask, and its corresponding kernel is WE in here. And also M has dimension of DHW is a mask features. The final segmentation mask will be upsampled via bilinear interpolation to 1 with respect to original resolution. So here, simply the mask branch, the upper branch here, in here, for example. So for mask branch, we can the segmentation mask for each instance can be directly produced by, we know the WE, which is created from the instance actuation branch, can be directly applied for mask branch in here. In here, for example, this one, the instance activation, that this is yeah, this is M, and this is the large M, and we can multiply it to get the mask branch here. Okay, so SparseInst outputs a fixed size set of predictions, and it's difficult to assign ground truth object with handcrafted rules. To tackle this issue, pairwise dice-based matching score C for ease prediction and cast ground truth object in this equation is applied, which is determined by classification scores and dice coefficients of segmentation. So we already have the output here. So where alpha is a hyperparameter to balance impacts of classification and segmentation and set to 0.8, and CK is termed as a category label for cast ground truth object, and PICK indicates the probability for category CK for ease prediction. M and T are the masks for ease prediction and cast ground truth object respectively. Here the dice coefficient is represented by this, where MXY and TXI denote the pixels at XY in the predicted mask M and ground truth mask T respectively. So we have our training loss is classified is here, L, so many L's here. This is a mask loss. LS is a binary cross entropy loss for EOY, aware objectness. Classification loss, mask loss, and binary cross entropy loss in here. So we have the total loss of our training model. These are the coefficients, by the way. Okay, so experiments, dataset, and evaluation metrics. We have COCO dataset and 100,000 images for training, 5,000 for validation, and 20,000 for testing. The evaluation is done on AP. It's a general evaluation metric. So for inference method speed, so we measure the frames per second. FPS, including the post-processing on NVIDIA 2018 Ti GPU. So here are the results. These are the other models here. Here is SparseInst. We have the backbone here, ResNet 50. And yeah, we have here ResNet 50. This This is the size of each features, and here are the FPS. As you can see, we have the FPS is highest among other models here. Also in AP evaluation metric, we have very good numbers and the results in here. And the comparison with state-of-art methods for mask AP speeds and calculators. Inference speeds of all models are tested on our machine. Can we know this? Okay, so we can see like with our backbone, different backbone, and like we got the higher score in both FPS and AP. So on decoder, we experiment application studies, and according to coordinates that brings in here, for example, coordinate denotes coordinates and deconvolution denotes deformable convolution. Adding coordinate brings 0.5 improvement with negligible latency. Replacing the last convolution with deformable convolution gives significant improvement on larger objects. Reducing the width or depth improves the inference speed, but lower the performance, while increasing the depth can further improve accuracy, but lower the speed in here. So for instance activation maps, we also experiment with 3x3 convolution and 1x1 convolution, and here with different activation maps. And here are the group convolution. And here using softmax or one-on-one convolutions brings 0.4 APA improvement and 1.2 APA drop respectively in here. And using 2 3x3 convolution brings no gain. However, group instance activation maps with 4 groups obtain 0.7 API improvement. Okay, so that's it. Thank you. By the way, I forgot to put like for feature results. If the objects are very dense here, SparseInst has some kind of difficulty. There are so many objects in the picture, its performance reduces. So in future, we need to deal with this. So that's the only limitation of SparseInst. Thank you.